In the last part, we saw how to use linear regression to find the regression line through the training points. But the data has some anomalies. What could be the reason that a 3-year-old car suddenly has low maintenance costs? It turns out the age is not the only factor in the equation. Dave pulls a new report from the system, and this time he adds the mileage to the data. And suddenly it gets clear. The mileage also plays a role in the maintenance cost. Dave decides to add the mileage as the second input to the system. Why do I say second? Technically, our network already has 2 inputs. One input for the age and one input for the bias. But schematically, it is not usual to show the bias as an input since its value is always 1. So we omit the bias input. The network has one input, the age. And now the second input for mileage is added. Here is the network diagram. The question is, what does the calculation in the neuron look like? Here it is. Weight of the age times age plus weight of the mileage times the mileage plus the bias. But most neural network diagrams generalize the inputs and weights by using subscripts like this. The weight belongs to the input connections of the neuron. The subscripts, or what is better known as indexes in Python, can become overwhelming once we start dealing with multiple neurons in multiple layers. I'll try to keep it as simple as possible. We learn an important lesson from this diagram. Each neuron can have multiple inputs but has a single bias. Later on, you will see neurons with hundreds of inputs, and yet each of these neurons will only have a single bias. I can imagine it is starting to get more complex with all this new information. So why don't I just add it to the code, which will make it much easier to see what happens? I start by adding the mileage to the training data. I'll paste a new training input set. Each input sample is now a tuple of age and mileage. I will replace W with W1 and W2. I chose the values arbitrarily. Until now, the predict function calculated with one input and one weight. I will now change this to support 2 inputs and 2 weights. Now I change the training loop to handle 2 inputs and 2 weights. Instead of a single weight D, I need 2 lists, one for each weight deltas. Weight 1D will have the changes with respect to the first input. Weight 2D will have the changes with respect to the second input. The question is, what are we going to print? I honestly don't know if printing weights and biases makes sense anymore, so I'll just delete them. I'll print the epoch instead. Okay, almost there. The only thing I need to do is update both weights. I delete the prediction at the end. That was a major change to the code. Let's see what happens. Python gives us an overflow error. The first thing I do is set epochs to 4 to see how the cost evolves from the start. You can see that the cost gets out of control rapidly. The changes to the weights and biases are too big. One way to control this is to decrease the learning rate. I'll add a few zeros here. The learning rate is still too big. I'll add even more zeros. We've got plenty of them. Now the cost goes down. I'll increase the epochs again. Okay, since the learning rate was so low, the amount of epochs needed to be high. The cost went down and I'm curious how well we are doing. Let me print the weights and bias after the training and execute the code once again. These weights and bias seem very low to me. Let's visualize the result. This diagram shows the age, mileage, and maintenance costs. As you have already seen, visualizing data becomes harder each time a parameter is added to the network. With 2 inputs and 1 output, we use a 3D graph to plot all the points. Here you see the 12 training data points. Linear regression with multiple inputs is called multiple linear regression. Instead of a regression line, we now have a regression plane. I plot it here, and now the relationship between inputs and outputs becomes clear. If I rotate the diagram a bit, you can see that the age has no significant influence on the price. Notice the red line, it does not rise. If I rotate it to the other side, you see that the mileage is responsible for almost all the changes to the maintenance costs. There could be many reasons why a network is not learning according to expectations. For example, if there is a very strong relationship between the inputs, the network is not capable anymore to understand the influence individual inputs have on the output. The technical term for this is multi-collinearity. It could be that this is the problem our network is facing. But as I said, there are many reasons that prevent linear regression from performing well. Before you start investigating the causes for such problems, always do this. Clean the data. One example of cleaning up data is dealing with missing data. We are not missing data, so this is not the problem we are facing. But perhaps we need to clean up our data otherwise. Look at the data. There are orders of magnitude difference between the age and mileage. Weight 1 needs to be 1,000 times larger than weight 2 to have significant influence on the maintenance costs. Dave suspects that the network ignored the age and just learned from the mileage. He decides to do a test. We know that a 1-year-old car with 20,000 miles should cost $750 per year. Let's make a prediction in the code. I expected 750 and got 675. Not bad. Let's do another one. This time I keep the age down and the mileage way up. The output should be around 1500. This is also not a bad prediction. But now let's see what happens when we crank up the age and keep the mileage low. Now we see a bad prediction. We expected 700 and got 338. We know one of the inputs is much more important than the other one. How do we make this a fair battle? This is achieved by normalizing the data. What is normalizing data? You'll see that in the next part.